Electromagnetic interference, or EMI, separation standards are crucial for ensuring the proper operation of electronic equipment. Several standards and guidelines address this issue, each offering recommendations based on different factors. Firstly, IEEE 61900.5 21997, which covers electromagnetic compatibility, EMC, Part 5, Installation and Mitigation Guidelines, Section 2, Earthing and Cabling, recommends a separation distance of at least 15 centimeters, or approximately 6 inches, between power cables and sensitive electronic equipment. Secondly, NFPA 70, the National Electrical Code, NEC, addresses EMI in Section 800.156, requiring proper separation of electrical circuits and systems to minimize interference. While the NEC does not specify a precise distance, it advises following the manufacturer's recommendations or utilizing good engineering practices. Thirdly, IEEE Standard 1100.2012, which is the IEEE recommended practice for powering and grounding sensitive electronic equipment, offers guidance for designing and installing power distribution systems to minimize EMI from power lines. This standard acknowledges that EMI sensitivity varies depending on the electronic equipment, but recommends a minimum separation distance of 6 inches or 15 centimeters for alternating current power lines. Fourthly, ANSI/TIE/IA 606. B. The Administration Standard for the Telecommunications Industry addresses grounding, bonding, and shielding for telecommunications facilities. While primarily focused on grounding and bonding, it includes information on EMI mitigation and recommends a separation distance of at least 12 inches or 30 centimeters between electrical circuits and sensitive equipment. In addition to these standards, several other considerations should be taken into account. Manufacturers' recommendations are important, as some electronic equipment manufacturers provide specific separation distance guidelines in their product manuals. Site-specific factors also play a significant role. The actual separation distance may vary depending on the type of electrical system, the sensitivity of the electronic equipment, and the physical layout of the site. Beyond separation distances, other EMI mitigation strategies can be implemented. These include shielding, which involves using conductive materials to block electromagnetic fields, grounding, which provides a low impedance path for fault currents and helps to reduce noise, filtering, which uses electronic components to attenuate unwanted frequencies, and proper cabling and routing, which minimizes the potential for EMI coupling. When implementing EMI mitigation measures, it is essential to consider the specific requirements of the equipment and the environment. A thorough assessment of the potential EMI sources and sensitive equipment is necessary to determine the appropriate separation distances and mitigation techniques. It's also important to remember that these are general guidelines. The optimal separation distance may vary depending on the specific equipment and the environment. Consulting with qualified engineers and following the manufacturer's recommendations is always a good practice. Consider the frequency range of the potential EMI sources. Higher frequency signals are more likely to cause interference, so greater separation distances may be required. Assess the sensitivity of the electronic equipment to EMI. Equipment that is more sensitive to EMI may require greater separation distances or additional mitigation measures. Evaluate the physical layout of the site. The presence of metal structures or other conductive materials can affect EMI propagation, so separation distances may need to be adjusted accordingly. Implementing a combination of separation distances and other mitigation techniques can provide the best protection against EMI. Shielding, grounding, filtering, and proper cabling can all help to reduce EMI levels and improve the performance of electronic equipment. Regularly inspect and maintain EMI mitigation measures to ensure that they are functioning properly. Grounding connections should be checked for corrosion or looseness, and filters should be replaced as needed. Consider using shielded cables for sensitive circuits. Shielded cables can help to reduce EMI coupling and improve signal integrity. Implement proper grounding techniques. A well-designed grounding system can help to reduce noise and prevent ground loops. Use filters to attenuate unwanted frequencies. Filters can be used to block EMI from entering or leaving equipment. Locate sensitive equipment away from potential EMI sources. This can help to reduce the level of EMI that the equipment is exposed to. Use surge protection devices to protect equipment from voltage spikes. Voltage spikes can cause damage to electronic equipment and can also generate EMI. Follow good cabling practices. Avoid running cables parallel to each other and use proper termination techniques. Ensure that all equipment is properly grounded. Improper grounding can create ground loops and increase EMI levels. Use shielded enclosures to protect sensitive equipment from EMI. Shielded enclosures can provide a high level of EMI protection. Regularly test equipment for EMI emissions. This can help to identify potential EMI problems before they cause issues. Keep abreast of the latest EMI standards and regulations. This can help to ensure that equipment meets the required EMI levels. When dealing with sensitive electronic equipment, understanding and implementing appropriate EMI separation standards is paramount. By adhering to guidelines from organizations like IEEE, NFPA, IEEE, and ANSI/TIE/IR, and by considering manufacturers' recommendations and site-specific factors, you can effectively mitigate the risks associated with electromagnetic interference. Moreover, implementing additional mitigation measures such as shielding, grounding, filtering, and proper cabling practices can further enhance the protection of your electronic systems. The importance of regular inspection and maintenance of these measures cannot be overstated, ensuring that your equipment continues to operate optimally in the face of potential EMI challenges. Always remember that a proactive approach to EMI management is key to maintaining the integrity and reliability of your electronic infrastructure. The specifics can vary greatly depending on the type of equipment and the nature of the electrical systems involved. For example, a high-frequency radio transmitter will require different separation and shielding considerations compared to a low-voltage lighting circuit. Consulting with experts in EMI mitigation is often the best course of action, particularly when dealing with complex or critical systems. These experts can perform site surveys, analyze potential EMI sources, and recommend tailored solutions to address specific needs. They can also assist in the design and implementation of shielding, grounding, and filtering systems. In addition to physical separation, other techniques can be used to reduce EMI. For example, using twisted pair wiring can help to reduce the amount of EMI that is radiated from cables. Twisted pair wiring consists of two wires that are twisted together. This helps to cancel out the electromagnetic fields that are generated by the wires. Another technique is to use shielded cables. Shielded cables have a conductive layer that surrounds the wires. This layer helps to block EMI from entering or leaving the cable. Filtering can also be used to reduce EMI. Filters are electronic circuits that are designed to block certain frequencies of electromagnetic radiation. Filters can be used to block EMI from entering or leaving equipment. Grounding is another important technique for reducing EMI. Grounding provides a low impedance path for electromagnetic radiation to flow to ground. This helps to reduce the amount of EMI that is radiated from equipment. Surge protection is also important for protecting equipment from EMI. Surge protection devices can protect equipment from voltage spikes caused by lightning or other electrical disturbances. Voltage spikes can damage equipment and can also generate EMI. Proper cabling practices are also important for reducing EMI. Avoid running cables parallel to each other and use proper termination techniques. Ensure that all equipment is properly grounded. Improper grounding can create ground loops and increase EMI levels. Shielded enclosures can be used to protect sensitive equipment from EMI. Shielded enclosures can provide a high level of EMI protection. Regularly test equipment for EMI emissions. This can help to identify potential EMI problems before they cause issues. Keep abreast of the latest EMI standards and regulations. This can help to ensure that equipment meets the required EMI levels. By following these guidelines, you can reduce the risk of EMI and ensure that your equipment operates reliably. Implementing robust EMI control measures is not just about compliance with standards, it's about ensuring the operational efficiency and longevity of your electronic investments. In today's interconnected world, where electronic devices proliferate every aspect of life, the potential for EMI is ever present. Therefore, a comprehensive and well-executed EMI mitigation strategy is a critical component of any modern technology infrastructure. Remember that EMI can manifest in various forms, including conducted emissions which travel along power lines and cables, and radiated emissions which propagate through the air. Addressing both types of emissions is essential for effective EMI control. Conducted emissions can be mitigated by using filters on power lines and cables. These filters block unwanted frequencies and prevent them from propagating through the system. Radiated emissions can be mitigated by using shielding, grounding, and proper cabling practices. Shielding involves enclosing equipment in conductive materials that block electromagnetic radiation. Grounding provides a low impedance path for electromagnetic radiation to flow to ground. Proper cabling practices include avoiding running cables parallel to each other and using proper termination techniques. In addition to these techniques, it is also important to consider the placement of equipment. Sensitive equipment should be located away from potential EMI sources. Potential EMI sources include power lines, transformers, and other electrical equipment. By taking these steps, you can reduce the risk of EMI and ensure that your equipment operates reliably. The cost of implementing EMI control measures is often outweighed by the benefits. EMI can cause equipment to malfunction, which can lead to downtime and lost productivity. EMI can also damage equipment, which can be costly to replace. By investing in EMI control measures, you can protect your equipment and avoid these costs. Furthermore, a proactive approach to EMI management can enhance the overall performance and stability of your electronic systems. By reducing noise and interference, you can improve signal quality and data transmission rates. This can lead to faster processing speeds and more efficient operation. In conclusion, EMI separation standards are an essential aspect of modern electronic system design and operation. By understanding the various standards and guidelines, and by implementing appropriate mitigation measures, you can protect your equipment, improve its performance, and ensure its long-term reliability. Remember to consult with experts, consider site-specific factors, and stay abreast of the latest developments in EMI control technology to maintain a robust and effective EMI management strategy.